Okay, so let's start with just a single voxel in the brain of one subject. And here, this is time going along the x-axis. So we've got 50 or so scans. And then this is the strength of the bold signal. And each red dot here is the actual measurement of the bold signal at that particular scan. And then what we've done is we've fitted a general linear model as described this morning, and then the fit of the model is shown with this green line here. And so this data was from a visual experiment where we had a rest period here and then some visual stimulation, and then in this particular voxel in the brain we get a response. And the size of that effect for this subject is 168 minus about 164, so the effect size is 4. So now let's look at another subject. Here, this subject has a smaller effect size, about 2. And typically you'd have 12 or so subjects in your analysis. And this is the 12th subject, and they've got a bigger effect size, this time about 4. So, given that we've got data from a whole group, then we can write down a list of what the different effect sizes are, and then look to see if the average effect size in that group, or the group effect, to see if that is significantly non-zero. So what you do is you just measure, compute the mean of those effect sizes, you compute the standard deviation. Now importantly here, this is the standard deviation over the group, so we're calling this the between subject variability. It's just simply the standard deviation of these numbers here. And then to see if the effect size is significantly non-zero, you just do a one-sample t-test, and what that does, it compares the effect, the group effect, to the standard error of the mean. So if you want to see the standard error of the mean is then just basically the between subject variability divided by the square root of the number of samples you've got. So here, number of samples is just the number of subjects. So our estimate of the mean effect is 2.67. Our certainty with which we can sort of measure that is 0.31. And then the t-statistic is just the ratio of the two. And so here we have a t-statistic of 8.6, and then that's basically highly significant. So this is known as random effects analysis, because we're comparing the group effect to the between subject variability. It's also known as the sort of summary statistic implementation of random effects analysis, because for each subject you're summarizing their response with just a single number, which is their effect size. Okay, so that's what we'd do to analyze group data. Another alternative approach, which you may have heard about, is called fixed effects analysis. So what that does is slightly different. So again, you're sort of looking at the effect sizes, and also another factor to take into account is the variability of the effect sort of within subject. So what that is to do with basically scanner noise, or equivalently, how well does your model fit. So, if you've got, say, a 7T system, you'll have a bigger effect size, but also your effect may be more variable. So this latter term here is to do with the noise on your scanner and how long you scan for, how many repetitions you get of each trial, or how many trials per condition. And sort of we put all those effects together and you end up with this number, which would be the within subject variability. So just looking at this particular subject, and crudely you can think of that as the quality of fit of the linear model. So if you look at the differences between the actual data points here and the model predictions, that would be an error at this time point, error at the next time point. If you square those and sum them all up over the whole time series, and divide that sum of squared error by the number of scans, take the square root, and you end up with this within subject variability. So for this particular subject, that would be, say, 0.9. For subject 3, we can see here that the model's not fitting so well in some parts of the time series. So on average, this subject has a bigger within subject variability than subject 1. And we can do this for all subjects. So subject 12, the model is fitting quite well here. So they have a lower within subject variability. And what we do then with the fixed effects analysis is effectively you just concatenate the time series from all the different subjects. So instead of now having 50 scans from one subject, you've got 50 times 12 scans, which is like 600 scans. And this is your whole study. And you compute the mean effect over all the subjects, and that actually turns out to be the same as it was before. And then you compute the sort of overall within subject variability, which is just like the average of all the each subject's within subject variability. So this was, say, subject 1, 2, 3, 4, 5. So subject 5, the model fits very well there, whereas with this subject 8, the model's not fitting so well. So we average all these, and this gives us our average within subject variability. And then we want to get the standard error of the mean. And so we divide by the number of sort of data points we've used to compute the mean. But here, this is very different than before. Here, this is now 600. So we've basically got this very long time series with 600 values, and which means the standard error is very small, and consequently, our inference about the mean is very strong. We end up with a huge t-statistic and a very, very significant p-value. So this is fixed effects analysis. And what we're doing here is we're comparing the group effect to the within subject variability. And generally in neuroimaging, this is not really the recommended thing to do, because it's not really what people would deem a proper inference about the group, because it doesn't take into account the between subject variability, and that's really what you should be testing against. Whereas with random effects, it does look at the between subject variability, so that if you were to have if you were to scan a new subject, then you could be confident that they would also have the same effect. So that's fixed versus random effects analysis. So another problem with these fixed effects analysis is, that these are sort of spuriously overconfident results. And this is kind of known in statistics as the fallacy of classical inference. If you have more and more data points, if you have hundreds and thousands of data points, then you'll almost always get a significant result. And this is known as the fallacy of classical inference. Basically, you can have a tiny effect size that would be have some smaller variability associated with it, and those two things don't quite scale properly. So basically, classical inference doesn't work if you have hundreds or thousands of data points. And so that's why it's not recommended in neuroimaging, because typically for each subject you'd have a few hundred scans, and then you'd have 10 or 20 subjects. And that's far too many for classical inference to work properly. And besides, you're not comparing the effect size against the correct quantity. Okay, there's also a third procedure, and that's called mixed effects analysis, which you would have probably heard about from using various statistical packages in other domains. And that's where some of your variables may be fixed effects, and other variables could be random effects. So, for example, in neuroimaging, you may want to treat the drifts that you heard about this morning, the size of those, as fixed effects, and then you'd have the effect sizes of the experimental conditions that you're interested in as the random effects. So that would be a mixed effects approach. Okay. So everything I've talked about so far was just for one voxel in the brain. It's completely straightforward. All you do is you you get the summary statistic from each subject, which is how big is the effect, and then you do a one-sample t-test. But of course, we've got images. We don't just have single time series, we have brain imaging time series. And so we just apply this, exactly the same procedure, but voxel by voxel at every point in an image. And so we take our data from subject 1, we fit a general linear model at every point in the brain, and then we apply a contrast vector, as you heard this morning, and this will basically summarize the effect at each point in the brain for each subject. And this produces what's called a contrast image. So you may have designed your experiment to test for, say, 3 or 4 different effects, and you could compute a different contrast image for each of those effects. And you repeat that for each subject. So here we've got a con image for our 12 subjects. And that's the end of what we call the first level of analysis. So then we do a sort of second level of analysis, where these con images then become the data for a second level analysis, where we just do a one-sample t-test at each voxel in the brain. And so you end up with a statistical parametric map showing these t-values here for positions where we have significantly non-zero effects. And so with this visual paradigm, we see activations at the back of the brain that are significantly non-zero over the group, so that if you were to scan another subject with the same paradigm, you could be confident that you'd also get activation in these visual cortices. Okay, so that's random effects analysis, and I've described an approach for implementing it called the summary statistic approach. It turns out that's not an exact method. There's a sort of gold standard and robust method, the gold standard method for doing random effects analysis is implemented using hierarchical models. And the sort of punchline is that with these hierarchical models, you take into account both the within subject variances and the between subject variances to make your inference. And with that way, you're sort of guaranteed the best results. So what are these hierarchical models? Well, this is the first level in a hierarchical model, and this is just the GLM that we've talked about this morning. So, so with the hierarchy, the first level parameters are then dependent on a higher level design matrix and some higher level parameters, and so on right up to some superordinate level. And then at each level of the model, we have variance components, and given some data, we want to estimate the effect sizes at each level and the variance components at each level. And then given that, we can then make an inference about the effects at any level in the hierarchy. Now this is a very general approach, and it's used for many things in SBM and brain imaging, so it's not just for group analysis of fMRI data. It turns out we can use the same approach here to do EEG source reconstruction, for example. But to give you the application of it to group analysis of fMRI, we just use a two-level model here, where this would be our first level design matrix and first level parameters and first level errors. And what we'd do is that our data would be all the time series from all the subjects. So here, our data vector y, here at one point in the brain, would be the time series from subject 1 in that column. And then below it would have the time series for subject 2 and then subject 3. Then the design matrix for subject 1 would contain all of those factors that we thought could explain the data for that subject. Similarly for subjects 2 and 3. And then the associated regression coefficients would correspond to the effect sizes for those subjects. And the variances of those errors would then be the within within subject variances for subject 1, subject 2 and subject 3. And then the effect sizes of the different subjects are then constrained to vary around a group effect size here, and that variability is specified using a between subject variance parameter. And so there's an algorithm called restricted maximum likelihood, which allows you to estimate the within subject variances and the between subject variances, the individual subject effects and the group effect all together in a recursive fashion. And that's implemented in SPM in the function SPM underscore REML, REML, that's for restricted maximum likelihood. And we can use that function to do mixed effects analysis, and it's actually implemented in SPM. It's called SPM underscore MFX, and here's the output of that that function, that analysis procedure, on some auditory data. So you have heard about the auditory data experiment this morning, and this is from a number of subjects or a number of sessions. And you can see that the results from the random effects analysis using the hierarchical model is just about exactly the same as the random effects analysis from the summary statistic model. And so this is really the gold standard approach. Why we generally don't use it sort of ordinarily is because it's computationally slow. So it's an iterative procedure. So to estimate all these parameters and variance components, you have to sort of start off with some initial values about what you think the individual effect sizes are, and then you estimate, okay, so what's then the within subject variance? How well do these first level models fit the data? What are these variances? Okay, and then you compute the group effect, and so you iterate between these parameter estimations in what's called an E step of the algorithm, an expectation step. And then in the M step of the algorithm, you estimate the variance components, and you iterate EM, etc. But because you've got so much data here, you've got all of the time series from all of the subjects put into one big model, it takes quite a long time to estimate all those parameters and variance components. Whereas when we do the simple summary statistic approach, because we sort of partitioned off the first level from the second level, and there's no sort of iteration back and forth, this is a lot quicker. So generally, because the results are the same and the summary statistic procedure is a lot quicker, people will use the summary statistic approach to do random effects analysis in brain imaging. Okay, and so you can question.
Can you repeat what do we gain by the hierarchical model? Sorry, can you repeat what do we gain from the hierarchical model with respect to the summary by using two levels with respect to one?
Yeah, so what you gain is that you're guaranteed to be doing the optimal analysis for each data set that you have. So you can show, one can show mathematically, if you look in, for example, a chapter in the SPM book, that on average, let's say you were doing 20 experiments the same, okay, you do the same experiment 20 times. Then you can show that if the within subject variances are the same, and if the first level designs are the same, then on average, the summary statistic procedure will give you exactly the same result as the hierarchical model. But if that condition isn't met, then they won't produce exactly the same thing on average. So the only reason you'd use the hierarchical model would be if you had within subject variances that were very different, or if you had first level designs that were very different. For example, if you had 20 trials for subject 1 and 2 trials for subject 2, that would mean that the subject 2's effect, really you should downweight that in your final analysis. And you can do that using the hierarchical model. So that would be the benefit of using a hierarchical model. If you don't have, if the number of trials, for example, is not under experimental control, for example, in epilepsy research, and you don't know how many seizures the subject's going to have. But generally, for more sort of vanilla neuroimaging applications, where we do have, we know how many trials each subject is going to have, to within 50%, and that sort of difference is not sufficient for you to get a significantly better answer with the hierarchical model approach. However, don't take my word for it. You can use the SPM-MFX function and see if you do get the same result. Okay, and there's also a recent paper by Tom Nichols and Jeanette Mumford, who have also shown that the summary statistic approach is indeed very robust in sort of practical imaging situations. Okay, just want to finish with slightly more sophisticated experimental scenario where you have multiple conditions. So what I talked about was just a simple visual stimulation experiment where you either had no stimulation or some visual stimulation. Obviously that's a crude caricature of the sort of things that we do, and more generally it might be the case that you have multiple experimental conditions. And if for example you have different conditions which are measured in different subjects, so for example a typical example here would be a drug design where you give someone a task to do, for example a memory task, and condition 1 it would be placebo, drug 1 and drug 2. And here you might want to have different subjects for drug 1 and different subjects for drug 2 in case there's any sort of interaction between the drugs. And to analyse the data here, you just do, instead of having a one sample t-test at the second level, you do an ANOVA at the second level. And then you could look for significant differences between groups, and then that inference would be a random effects inference. In other words, it would apply to the populations from which these subjects were drawn. A slightly more complex situation is where you have the different experimental conditions are measured in the same subjects. So here, this could be a different sorts of memory tasks. For example, you may have NBAC working memory tasks, and you may get subjects to want to see if the current item is the same as the last one, or the second one before, or the third. So you might want to look at an effect of memory load, for example, and you would measure each level of load. You'd measure 3 levels of load, say in subject 1 and in subject 2 and in subject 12. And to analyse this data, you'd use an ANOVA within the subjects. And this is just the same as an ordinary ANOVA, it's just that you subtract out the subject effects. And if you only have 2 conditions, this is just the same as doing a paired t-test. And generally, you'd want to have your manipulations within subjects if that's at all possible, because you'll get more sensitive results, because you've controlled for many more things than otherwise. Okay, so just to summarise, group inference usually proceeds with random effects analysis rather than fixed effects. And that's because we're comparing the effect size to the between subject variability. And the best way to implement a random effects analysis is to use a hierarchical model, but it's pretty computationally intensive, and for most applications in neuroimaging we get the same results with the fixed effects approach. But if you have a niche application where you have very different numbers of trials for different subjects, and here I'm talking about by an order of 10, then you may want to use this SPM-MFX function that implements the hierarchical modelling. Otherwise, for the rest of us, for the 99% of us, summary statistic methods are a robust method for implementing random effects group inference. And if you've got multiple experimental conditions, then you can use, instead of a t-test at the second level, you can use an ANOVA between subject or within subject. Okay, thank you very much. Any questions? Well, that's never happened before. I trust it was a good lunch.
So where is the SPM MFX button?
In production. It's my fault. I promised Guillaume it will be ready by this lecture, but it's not.
Are you serious?
Yes, yeah. All you need to do is you need to make a big fixed effects design. So in a fixed effects design, it would look like this, except you'd have the X2 underneath the X1 and the X3 underneath the X2. So if you make a big fixed effects design, which is what people used to do 10 years ago, then that would be your input to the SPM MFX function. And then it will shift this over, and then it will create a second level design matrix, and then it will apply REML to that. So, yeah. So in SPM 11, it will definitely be in. Question?
For a one sample t-test, if you're planning to do that, can you go directly to second level rather than?
Yes, yeah, exactly. So if you have PET data, for example, then or if you've done some EEG analysis before, then you go directly to the second level. Yeah.